Welcome to this explainer. Today, we're diving into the ultimate solar system cold case. We're looking at a mission designed to travel back in time, figuratively speaking, of course, to uncover the 4.5 billion-year-old secrets of our planetary neighborhood. I am absolutely thrilled to guide you through the grand scale and the incredible precision of NASA's epic Lucy mission.
Here's our flight plan for this explainer. We'll be covering fossils of the solar system, meeting the Lucy spacecraft, its 12-year epic journey, the Quetta surprise, and finally, the Patroclus Menoetius binary.
Okay, let's dive into this. Just imagine a 12-year epic space odyssey. This is a mission defined by unprecedented ambition, the very first spacecraft ever dedicated to exploring the Trojan asteroids. It's a journey that pushes the absolute limits of celestial navigation and really, human ingenuity.
Section 1. Fossils of the Solar System, the Trojan Asteroids.
So these targets are essentially a time machine. The swarms of asteroids leading and trailing Jupiter in its orbit, known as the L4 and L5 Trojans, well, they aren't just some uniform group of space rocks. They are incredibly diverse fossils. They have different colors, different sizes, and totally different albedos, which just means how much light they reflect. By surveying all this diversity, scientists can actually constrain their models of exactly how the giant planets migrated back in the early days of our solar system.
Section 2. Meet the Lucy spacecraft, built for discovery.
Now, you can't have an epic journey without a capable hero to make the trek, right? Just marvel at the engineering of this spacecraft for a second. To operate all the way out past Jupiter, where sunlight is scarce, Lucy relies on those massive, gorgeous solar arrays. It's a beautifully designed machine built for a single, highly complex survey, and it's carrying a very specific set of tools right there on that payload platform nestled in the center.
And here is exactly what it carries. Lori gives us high spatial resolution imaging, basically so we can see the surface geology. LaRalph is our color and infrared spectrometer to map out surface composition. Then there's LTESS, which literally reads the temperature of the asteroids. T2Cam tracks the targets as we fly by, and the high-gain antenna allows scientists to measure Doppler shifts. That last one is super important because it helps them figure out the interiors and the masses of these ancient rocks.
Section 3. A 12-year epic journey, 4 billion miles.
Now that we know the machine, we really need to grasp the sheer, breathtaking scale of the route it has to take. Just think about this. 4 billion miles. 12 years. All of this time, effort, and engineering for a series of flybys where the closest approaches only last a matter of hours. I mean, the tactical absurdity and the awe-inspiring dedication of committing 12 whole years just to collect a few hours of high-resolution data, it's truly a testament to how valuable these planetary fossils actually are.
And this brilliantly illustrates exactly how complex that route is. Lucy doesn't just shoot straight for Jupiter. It loops around Earth for gravity assists, flings way out to the L4 Trojan swarm to visit targets like Eurobetes and Orgulus, and then actually falls all the way back toward Earth for another gravity assist, just so it can be slingshotted out to the L5 trailing swarm. It is a masterful, carefully orchestrated orbital dance.
To ground that complex map in reality, here is what the chronological timeline looks like. Lucy flies by the main belt asteroid Donald Jonassen in 2025, reaches its first Trojan target, Eurybates, in 2027, and finally arrives at its culminating destination, the Patroclus Menoetius binary, in 2033.
Section 4. Eurybates and the Quetta surprise. Target of opportunity. You know, sometimes in science you get a thrilling bonus before you even arrive. Eurybates is a C-type Trojan, roughly 64 kilometers across. But after the mission was already completely planned out, the science team used the Hubble Space Telescope and actually found a tiny 1-kilometer satellite orbiting it, which they named Quetta. It's this incredible target of opportunity that Lucy will now get to observe as a total bonus when it flies by. Section 5. The Patroclus Menoetius binary. The grand finale.
So this is where the orbital mathematics get highly analytical and incredibly fascinating. What we have here is an artist's conception of Patroclus and Menoetius. This is the first known binary Jupiter-Trojan. It's a near equal mass system where the two massive bodies actually orbit a shared center of gravity, literally taking turns eclipsing one another.
We actually already have incredibly precise data on this system from telescopes right here on Earth. With an orbital period of about 4.28 days and a tightly bound semi-major axis of 688 kilometers, scientists have been able to calculate their mass.
By combining that with thermal observations, they figured out the bodies have a very low mean bulk density and a low surface thermal inertia, which honestly is just a fancy way of saying these objects are incredibly porous, likely covered in a deep layer of fluffy, fine-grained dust, or regolith.
So, the absolutely crucial point is how we get this data in the first place. It's all thanks to something called a mutual event season. Because of how their orbit is tilted, the plane of the Patroclus and Menoetius binary aligns with Earth and the Sun just twice during their 12-year orbit around the Sun. When this happens, we can actually watch them physically pass in front of or cast shadows upon each other.
By measuring exactly when the foreground object occults, meaning blocks the view of, the background object, and when it casts an eclipse shadow onto it, scientists can refine the orbit of this binary pair down to an insanely precise degree. They test for things like whether the orbit is perfectly circular or if it has any eccentricity to it.
Let's see how this all builds to the actual mission. All of those complex shadow models matter because astronomers use them to bridge the gap between deep space and our telescopes here on Earth. They are observing these tiny light dips right now to ensure that when Lucy finally flies past Patroclus and Menoetius in 2033, the cameras are pointing at the exact right coordinates, literally down to the millisecond. The human ingenuity required to plan this 12 years in advance is just spectacular.
Which leaves us with this final thought. We've mapped the trajectory, we've modeled the shadows, and we know exactly where we're going. But if the Hubble Space Telescope could discover a tiny moon like Quetta completely by accident after the mission was already set in stone, what else is hiding out there in the dark waiting for Lucy to fly by? The outer solar system is vast, and I, for one, absolutely cannot wait to see what surprises it holds.